All right, so let's look at what happens during a collision between two bodies. So you've got this block. Maybe it's like a hockey puck or something on a smooth surface, and it's going to collide with another one. And maybe this is object 1 and this is object 2. And object 1 is moving to the right and object 2 is moving to the left. They don't have to have the same velocities, just moving towards each other. Now, when they collide with each other, they touch each other. So 1 would be in contact with 2. So I'm going to draw them right up against each other. So they're in contact with each other. This is object 1 and this is object 2. And there's this crash that's happening, crash type thing that's happening. And during that crash, they touch each other. Like, that's the whole idea behind a collision. So does mass 1 put a force on mass 2? Does mass 2 put a force on mass 1? So mass 1 applies a force. So the force on 2 from 1 on 2. Get my lines there, right? And then 2 applies a force on 1. So 2 on 1. Now what did we probably learn in middle school about these two forces between two bodies? Newton's third law is that for every force there is an equal and opposite force between two bodies. So the force 1 on 2 should be equal but opposite in magnitude to the force of 2 on 1. Now, if that is true, and I take this idea that the force of 1 is equal but opposite to the force on 2, and if that is the only force acting in the horizontal direction during the collision, so we're on a frictionless icy surface, then mass 1 will have an acceleration and mass 2 will have an acceleration. So if you've got a fly and you have a big giant Mack truck, and the big giant Mack truck is coming towards the fly, okay, and it has a velocity, it's going this way, or maybe it's not even moving, but then this guy is moving this way. During the collision, which object experiences the greatest force? Is that what Newton thinks? What is? They're equal but opposite. That's right. So maybe the mass of the bug. So this is the bug, and this is the big truck. Okay. Maybe the mass of the bug is really small. And the mass of the truck is really big. So then the acceleration of the truck would be really tiny. But the acceleration of the bug would be really big. And that enormous acceleration is too much for the bug's little exoskeleton. And it splats. Just like if you accelerate at a very high rate, then your bones can't hold you up either and you will splat. Spaghettification. Don't go close to black holes. Okay, so it's a difference in accelerations. It's not a difference in forces because they have different masses. Okay, so let's do some substitution then. So if m1 accelerates, then that means that there's a change in velocity of object 1 over time, which would be equal but opposite to the mass times the change in velocity of object 2 over time. Now, the time for those collisions, does M1 touch M2 for longer than M2 touches M1? Same time. Think about it. If you touch the table and then untouch the table, did you touch the table for the same amount of time that the table touched you? Even though that was a low-key collision, it was still a collision. There was a force between them. And so the time could actually cancel out on both sides of this equation, and then we're left with m1 delta v1 is equal to negative m2 delta v2. Now at this point, maybe that looks familiar. Maybe that looks like the momentum or the change in momentum of object 1 is equal to the negative change in momentum of object 2. Now if I wanted to continue though, then could I write this as m1 times v1 minus v1 initial is equal to negative m2 times v2 minus v2 initial, where I've just expanded what the deltas are, and each object has its own initial and final velocity. Then I could distribute the m, so m1 v1 minus m1 v1 initial is equal to negative m2 v2 plus, because I have a negative times a negative, m2 v2 initial. Now let's get all the initial velocities on one side and all the final velocities on the other. So I could m1 v1 can stay here. I can add m2 v2 to both sides. And I can add m1 v1 initial to both sides and leave m2 v2 initial on the right side. So what does m1 v1 mean? You found the product of m1 times v1. So this would be p1 plus p2 is equal to p1 initial plus p2 initial. When you add things together, what's the fancy word for adding things together? Sum. Yes. So the sum of the final momentum is equal to the sum of the initial momentum. So during the collision, the initial momentum is equal to the final momentum. It is the same. There is no change. What do we call that sort of interaction? It didn't change. It is constant, but there's a word for when there's nothing lost or nothing transferred. It's conserved. So this is the conservation of momentum. Now, the catch is this. Momentum is only conserved only if there are no external forces acting on the system or the bodies. So that means that at the moment of collision, the only forces in the direction of the collision, the only forces have to be the interaction forces. So that means that your free body diagram would have to look like, here's object 1. There's the force of 2 on 1. Object 2, there would be the force of 1 on 2, but you know it's on the earth, so there's a gravitational force. It's on a track or icy surface, so there is a normal force. a perpendicular force. There is a normal force and a gravitational force here. Are those forces, those vertical forces, are they in the direction of the motion that's changing? No. And if momentum is a vector, then because the forces are a vector, there's no change in momentum in the vertical direction, because what was the velocity in the vertical direction of each one of these blocks before they collided with each other in the first place? 0. They were only moving in the x direction. So these forces, even though they are external, they're not in the direction of the motion. So an example of a force that could be present in a collision that is parallel to the motion would be what? It's hard to get rid of it. Friction. Okay, so if there's friction, momentum is not conserved. It may be very, very close. It may be so close, though, that it's enough that we can prove something that we're looking for. So we use conservation and momentum in all kinds of scenarios in real life. And most of the time, the collision force is so much greater than the friction force that it's almost negligible. So when we do activities, when we do our lab starting tomorrow, we will have to neglect friction because we do not have any way to measure it. Okay? But the fact that we are on Earth and it's not perfect and we have a track with little carts means that there is going to be an external force. So it's one of those expectations that we should get a number that's close, but we should know why it's not close. Okay? So if I were drawing the force versus time graph for this collision, and I'm going to use blue for the force on 2, and I'm going to use green for the force on 1. Look at the direction of those forces. If my force sensor was going to measure direction and time, what would the force graph on 2 look like? Is it a positive force, negative force, or 0 force? Which way is it pointing? To the right? Yeah. This force is pointing to the right, so I would imagine that my force would look like whoop, whoop, like that little weird noise I made there. So then what would the force versus time look like for this first mass? It should look like maybe like the mirror image of it. Pretend like I can do that, because apparently I cannot. Whoa. Whoa. Oh, okay, whatever. Come on. Just wants to scroll too much. Whatever. Okay, so anyway. So pretend like those are the same. So what's the big idea, though? What does the area between the green graph and the time axis represent? What does the area between the blue graph and the time axis represent? This is the impulse. This is the impulse. And if the change in momentum of 1 is equal but opposite to the change in momentum of 2, then the impulse, and the symbol for impulse is a script J, is equal but opposite to the change in for the impulse for the other one. So this is just a fancy way to write impulse. It's a J. Wait, can you do the first thing? Okay, it's in the link.